Hey everyone, and welcome. Have you ever stood in a pharmacy and wondered how that generic version of a medicine gets the green light? How they can be so sure it works? Well, it's a really fascinating mix of chemistry, biology, and some super clever scientific shortcuts. Today, we're going to crack that code. Let's dive in.
So this is the big question, right? For a generic drug to get approved, regulators have to be absolutely certain it'll do the exact same thing in your body as the original brand name one. But think about it. Running massive, expensive human trials for every single generic drug would take forever and cost a fortune. There's got to be a smarter way.
And you bet there is. Way back in 1995, scientists came up with this brilliant framework to solve that exact problem. It's called the Biopharmaceutics Classification System, or BCS for short, and honestly, it was a total game changer for getting affordable drugs to people.
So at its core, the BCS is all about prediction. It's a way for scientists to use pretty simple tests in the lab to figure out how a drug is going to behave inside the super complex environment of your body. This means they can get the answers they need without always having to do those long, complicated studies with human volunteers.
The whole system really rests on two main ideas, two pillars: solubility and permeability. The easiest way to think about it is like making a cup of coffee. Solubility is all about how easily the drug dissolves, like sugar dissolving in hot water. And permeability, that's how easily the drug can pass through the walls of your intestines and into your bloodstream, kind of like coffee passing through a filter. And the science here gets really specific, which is pretty cool. For a drug to officially get the label highly soluble, its highest possible dose has to completely dissolve in 250 milliliters of water or less. To put that in perspective, that's about the amount in a normal coffee mug. It's a really simple, clear, and measurable standard.
And the bar for permeability is just as high. A drug is considered highly permeable only if scientists can prove that over 90% of the dose you take actually gets absorbed into your system. This is huge because it tells them the drug is really good at getting from your gut to where it needs to work its magic.
Okay, so when you take these two factors, how well a drug dissolves and how well it gets absorbed, you can sort pretty much any pill into one of four distinct groups. I like to think of them as drug personalities, because each one tells you exactly how that drug is going to behave once it's in your body.
And it all lays out in this simple 2x2 grid. On one axis, you've got high and low solubility. On the other, high and low permeability. And just like that, you get our four classes: Class 1, Class 2, Class 3, and Class 4. Each one comes with its own unique challenges and, of course, its own strategies for the drug makers.
Let's start with the best-case scenario, the A-team, Class 1 drugs. These are the all-stars of the drug world. They've pretty much got everything going for them, which makes them, by far, the easiest to work with.
Class 1 drugs, like ibuprofen or acetaminophen that you've probably taken, they dissolve easily and they get absorbed easily. They check both boxes with flying colors. Because of that, making them into a pill is pretty straightforward. You don't need any fancy delivery systems. A simple, well-made tablet or capsule gets the job done perfectly.
All right, next up we have Class 2. These drugs are a little more of a challenge. They're kind of like a stubborn sugar cube that just refuses to dissolve in your iced coffee, even though you know it'll work great once it finally does. So the key thing with Class 2 drugs like diclofenac is they have low solubility but high permeability. What that means is, if you can just get them to dissolve, they'll get absorbed into the body no problem. The whole strategy here is to boost that solubility. A really common technique is called micronization, which is a fancy word for grinding the drug particles down to be incredibly tiny. Think about it. Powdered sugar dissolves way faster than a sugar cube, right? Same idea here.
Now let's talk about Class 3, which has the exact opposite problem. These are the poor travelers. They dissolve beautifully, like instantly. But then they have a really tough time actually crossing that intestinal wall to get into the bloodstream.
So, for drugs like atenolol, which are highly soluble but have low permeability, dissolving isn't the issue. The real challenge is absorption. So, the strategy involves using special ingredients called permeability enhancers. They basically act like a key, helping to open the door so the drug can pass into the bloodstream more easily. And that brings us to the final boss, Class 4. These drugs are the toughest of them all. They present this double whammy of problems for scientists trying to turn them into an effective medicine.
Yeah, Class 4 drugs like furosemide have the worst of both worlds: low solubility and low permeability. They don't dissolve well, and they don't get absorbed well. To make these work, you have to throw the kitchen sink at them. It often requires a combination of really advanced strategies to tackle both problems at the same time. So, we've gone through all these different personalities. You might be wondering, why does all this classification really matter?
Well, this is where it all comes together. This is the big payoff. This system isn't just some academic exercise. It has a huge, real-world impact. This is our scientific shortcut.
And that payoff has a name, the bio-waiver. It's pretty much what it sounds like. It's a waiver from having to do those big bioequivalent studies in humans. For certain really well-behaved drugs, regulators can say, you know what, we've seen enough from the lab data, you're good to go. This saves an incredible amount of time and money, and it's a huge reason why generic drugs are so much more affordable.
So how do you get this fast pass? Well, there are 3 main hoops to jump through. First, the drug has to be one of those Class 1 all-stars. High solubility, high permeability. Second, the generic pill itself has to dissolve super fast in the lab. And third, all the other stuff in the pill, the inactive ingredients that hold it together, the excipients, they have to be proven safe and can't get in the way of the drug's absorption.
Okay, but as amazing as this system is, it's not a magic bullet that works for every single drug. It's time for a little reality check, because the BCS does have some important limitations that scientists and regulators are still working through.
The biggest thing to remember is that those bio-waivers, that fast pass, it's mostly just for those easy-to-handle Class 1 drugs. The more challenging drugs in Classes 2, 3, and 4, they almost always still need those expensive in-person studies. On top of that, different countries have slightly different rules, which can make things tricky. So it's a fantastic system, but it's not perfect.
And this quote really just sums it all up perfectly. The BCS absolutely revolutionized the drug development process. No question. It made things faster and cheaper for everyone. But the next big frontier is getting all the regulators around the world on the same page to harmonize the rules and make the system even more powerful.
And that leaves us with this one really critical question for the future. As our medicines get more and more complex with new technologies and new delivery systems, how will scientific frameworks like the BCS need to change and adapt? It's a huge challenge, but it's one that will define the next generation of science and help make sure that even the most advanced medicines can be affordable and accessible to everyone who needs them.